Now that we know about complex numbers, how to multiply them and add them and subtract them and divide them, and also put them into different forms and do those same operations, now we can look at solving some equations. Now there's many equations that have complex numbers in them, and heaps of them are actually beyond the scope of what we're studying at the moment. So what we're going to do here is focus on a specific type of equation, and that specific type of equation is finding the roots of complex numbers. So what I mean by that is just something like finding what's z if z to the 5 is equal to 1, or maybe something like what's the cube root of 2 plus I. These kind of things. They're the kind of equations that we're going to solve here. Let's just think about it for a moment. Let's just say we know that z is given in exponential form like this, mod z e to the theta I. And I say, well, what's z to the 1 on n? Some sort of root, like a square root or a cube root or something. Can we just say that it's the modulus raised to that power and then the angle divided by the power, or multiplied by 1 on n if you like? Kind of, but that doesn't give us the complete picture. So remember for a minute back when you did just regular old numbers. If I said, if I know that x squared is equal to 4, then we could say, well, x is equal to plus or minus the square root of 4 plus or minus 2. There were two answers for a square root. Well, it turns out that there's this fundamental theorem that says whenever you're finding the nth root of a complex number, there'll always be n possible values. So for example, a square root will always have two possible complex valued solutions. Cube root will always have three possible complex valued solutions. So just doing this right here is not going to give us the whole picture. It only gives us one value. So we have to be able to figure out what the others are. And it all goes back to when we first started defining what a polar or exponential form was. Remember we said that the argument of z, that is given by the equation tan theta is equal to y on x. And we said that theta is actually not unique, because when you go around a circle, if you say sitting out here, that's theta, well, you could actually go around the whole circle and back again, add 360 degrees to it, or add 2 pi if you like. Or you could have gone back around the other way, taken away 2 pi from it. There's infinitely many angles that will give you the same complex number, but we just happen to have chosen to use the principal argument. So what we're going to do now is actually call back all of those other possible solutions, or possible arguments. So we've got infinitely many representations of z using all of the possible different values for the argument. Theta itself, plus 2 pi, plus 4 pi, and so on, or minus 2 pi, minus 4 pi, and all the way back to minus infinity. So in other words, we can say our complex number, if we're not worried about a unique representation, is given by the modulus of z and then e to the theta plus 2 pi times an integer, k, where k can be 0, plus or minus 1, plus or minus 2, giving us all of these values here. So we've got mod z e to the theta plus 2k pi I. So for example, if we had k equals 0, we've got z is equal to mod z e to the theta I. If k is equal to 1, z equal to mod z e to the theta plus 2 pi times I, and so on. But all of these are actually the same number, because theta, theta plus 2 pi, same angle, right? So we can keep getting those, as many as we want. We're going to use these extra representations to allow us to generate the extra solutions to our root problems that we couldn't find just by using that power rule up the top there. And what it comes down to is basically this rule here: nth roots of complex numbers. Given our complex number in exponential form, as I said, that fundamental theorem says z always has n complex valued nth roots, and they're given by this rule right here. Z to the 1 on n, or the nth root of z if you like, is, well, it's always the nth root of the modulus, that real value, and then it's e to the theta plus 2k pi on, times I divided by n for each of the numbers k equals 0, 1, 2, all the way up to whatever n minus 1 is for our particular problem. So let's just say we're talking about a cube root, z to the 1 on 3. What we'd do then, we'd talk about using k equals 0, k equals 1, and k equals 2. and we stop at 2, because if 3 is our n value, n minus 1 is 3 minus 1 is 2, so we have that. And you can see there we've got 1, 2, 3 different values that we're going to use. So it gives us our 3 complex valued nth roots. And the values are given by the modulus of z to the 1 on 3. Well, that's the same for each of them. And then e, and we have to go theta plus 2k pi. If k is 0, theta plus 2k pi is just theta. I divided by 3. And then if k is 1, we've got theta plus 2 pi. I divided by 3. And with k equal to 2, we've got theta plus 4 pi. I divided by 3. So that would generate our 3 values for the complex valued cube roots of any number z. Now you might think, well, why don't I keep going? What about all those other values? Well, it turns out, as you might expect, it actually just loops back around and starts giving you the same values all over again. And the same if we've gone backwards to -1, -2, and so on. We'd just be generating these same 3 cube roots for whatever the number z is. So basically, finding the nth roots is just a matter of applying this rule. So let's check it out. Here we've got a question that says, w to the 4 is 1 plus I, find w. So in other words, you could think of that as saying, well, what's the 1/4 root of 1 plus I, if you like. Okay, so thinking back, 1 plus I to the 1 on 4, that's essentially saying that our number z here in the rule is 1 plus I. But the rule only works for exponential values, or exponential forms, sorry. So we need to find 1 plus I in exponential form. Now I think we've done this before, but basically, exponential form, we need the modulus, which is the square root of the real part squared and the imaginary part squared, which is going to give us the square root of 2. And theta is going to be found by finding the inverse tan of y on x, or imaginary on real, 1 on 1. Or if you like, just by knowing that the number 1 plus I in the Argand diagram sits up here directly at a 45-degree angle. It's 1 and 1 are its real and imaginary parts. So that's going to be pi on 4, or 45 degrees if you want. So our angle, sorry, that's not an implies, that's an equals. Theta is equal to pi on 4. So z is equal to root 2 e to the pi on 4 I. So that's our complex form. So now we've got our z in exponential form, and we need its 1/4 root. So our rule from the previous page says that z to the 1 on 4 is going to be the modulus of z to the 1 on 4, e to the theta plus 2k pi times I over 4, where k is going to be equal to 0. Remember, it goes up to n minus 1. 0, 1, 2, and 3. 4 minus 1 is 3. And that's going to give us our 4 possible values for our 1/4 root. So let's jump over on the next page and have a go at that. So with k equal to 0, we're going to have z to the 1 on 4 is equal to square root of 2 to the 1 on 4, and then e to the theta plus 2k pi. Theta plus 0, so that's just theta, and if we remember back, theta is pi on 4 times I. So that's one of our values. K equal to 1 is going to be z to the 4. If you like, you can put little subscripts down here, 0 and 1 or whatever, but I'm not going to bother with that because they're all just values of z to the 1 on 4. So again, we've got root 2 to the 1 4. Remember, root 2 is just 2 to the half, so 2 to the half to the 1 on 4. Let's actually write that as 2 to the 1 on 8, just to make it a bit neater. 2 to the 1 on 8. We can do the same up here as well. 2 to the 1 on 8, e to the, remember it's theta plus 2k pi I on 4. So we've got theta is pi on 4 plus 2 pi. Pi on 4 plus 2 pi. It's going to be 9 pi on 4, I think. and then we've got to divide that by 4 again. 9 pi on 16 I. I can see I've made a mistake up here. I've forgotten to divide this angle by 4. I've just got theta there, whereas it should be theta plus 0 I on 4. So that's going to be a 16 in there as well. So I'll just fix that one up. So it's pi on 16 I. Now k equals 2. Why don't you pause the video for a sec, have a go at k equals 2 and k equals 3, and I'll stop for a couple of seconds and I'll fill those in and come back in a moment. Okay, so there we have our k equals 2 and k equals 3 values. 2 to the 1 on 8 stays the same all the way throughout. That doesn't actually change, just the angle does. So you may have just written down 17 pi on 16 and 25 pi on 16. The only thing I'll ask you to do here is remember that we like to put our arguments in principal argument form, so between minus pi and positive pi. So what I've just done there is converted that back to a principal argument form. So we've got our 4 possible values. Remember we said that there would be 4 values for a 1 on 4th value, 1 on 4th root. And there they are there. So we've got four roots. So those values, going back to the question, are the possible values of w that solves this equation. Okay, so that's solving equations, or roots with complex numbers. An example of that. There's a heap of neat stuff that goes on here. If you actually draw these, you'll find that they form their points form the corners of a perfect square. Because there's 4 of them, they'll form a perfect square every time. If this was a 5th root, they'd form the corners of a pentagon. If it was a 3rd, a cube root, they'd form the corners of an equilateral triangle, and so on. And also you might notice that once you've actually figured out where you are here and here, those are different by 8. Okay, same here, goes up by 8, 9 to 17. This one goes up by 8. So they're always equidistant around around the origin. So they've got to form a 360-degree rotation together. So you can just split that up into 4 pieces, and you can actually just generate each of the subsequent values without calculating them with the rule. But the rule's there if you like to use it. Anyway, lots of interesting stuff to check out. Just to finish off now, you can check out section 3.3 of the text if you like, or a similar section in any other text. Attempt the exercises from the worksheet, and also section 3.3 of the text. There's some questions in there too. And as always, check out your queries with either your workshop tutor, lecturer, or the Folk in Stimulate. But that's it for this set of videos.